Hello, my name is Constance and this is Dynamic World. I'm going to start this video off with a brief description of our project, and then Leo will give a demo. Our project is to simulate a world in which animals interact with each other and compete for resources. The environment is represented as a grid of cells. Each cell has a terrain that is represented by a specific color. A cell may contain resources. The type of resource is determined by the terrain, and there are no restrictions on the amount of each resource. Resources are dynamic. They disappear when animals consume them and regenerate over time. Here is a picture of our environment. The yellow region is the desert. The black square in the top left corner denotes the absence of resources. We have also listed the characteristics of the environment. Notably, the environment is partially observable. The agent can learn about the cell it is currently in, but cannot discern any surrounding cells, unless they had previously been visited. Since the environment is partially observable, the agent needs to maintain internal state to keep track of the world. There are 3 animals in our environment: tigers, giraffes, and elephants. They all consume resources scattered throughout the world. In addition, tigers can eat both giraffes and elephants. We have 2 versions of the GUI. One in which the animals are represented by colored squares, and the other in which we have pictures of the animals. The animals are modeled as rational agents, and their performance measure is how long they survive. At a given time step, an animal perceives the resources and terrain of its cell, as well as the animals in that cell. As animals move around the world, they keep track of all cells they have visited. Initially, an animal is only aware of the cell it starts off in. We model the animals as goal-based agents. The goals an animal can try to achieve are explore, meaning move to a new, possibly undiscovered cell, eat, drink, mate, and sleep. Some of these goals are necessary to the animal's survival, such as eating and drinking. Others, such as mating and exploring, are not. Now it's time for the demo.
Hi, my name is Leo. So, let's get our simulation running. As you can see, we have our command bar with different commands for running the simulation. We have our visualization of the world. As we discussed, each of these different cells is colored based on its type of terrain. When we click on any given one of these cells, we get a little pop-up about the information of that cell. For instance, the one that we clicked on was a plane, and it had this location, row 6, column 4, and it had 5 grass. So if we click on a cell that has an animal on it, such as this desert here, we can see that it prints out the information about that animal. The orange square there is an elephant, and as you can see here, the elephant has no hunger and no thirst, and it has full energy, which is 11. So when we close that and we step forward the simulation, we can see that the animal has moved and the time step has increased in the world. Furthermore, we can see that the goal of this animal is to explore. As discussed, these animals are goal-based agents, and so every step they determine which goal will satisfy their needs, and then they act to achieve that goal. So right now, as we keep stepping, we will see that this elephant, has the intention of exploring. And it will do so until a point where his needs have changed. So now that he is hungry and thirsty, he's going to try and meet his new needs. So if we step once more, we can see that his new goal is to drink because he was thirsty. So now if we click on him, we can see that because he drank, he no longer has any thirst. So as you can see, his goal has now changed to eat, so he'll head over to a square that has food on it, and then he will eat, thus changing his hunger back to 0. With that, you can see that he's going to continue to explore, continue to drink, and continue to eat whenever those needs arise. And in that fashion, if we step quickly through the simulation, we can see him dancing around the world, looking for new cells to go to, and drinking and eating as he goes. Here you can see a more complicated version of our simulation. Instead of just one animal, we have 20 animals of each species. When we run this simulation, you can see that there are many more things that happen at once, and for the sake of simplicity, we haven't printed out each of the animal's goals. However, each of these animals is acting independently as a rational, goal-based agent. Every time step, it determines a goal that will satisfy its needs, and it will try to achieve that goal. As we step through, we can see that certain events are occurring. For example, an elephant and a giraffe have recently died, as indicated in the console, and as we keep going, more of these events will continue to happen. Namely, the giraffes and the elephants are prey to the tigers, and so will be eaten by them. As we step faster through the simulation, we can see that most of the elephants and tigers, in fact all of them, eventually die out, and all that's left is the tigers. However, this is actually an issue because as we continue to step, we can see that there is now issues in contesting for food. As we continue to step, you can see that tigers are now dying of hunger and the number of tigers is decreasing. As we step faster and take more time, the simulation results in fewer and fewer tigers existing, and if we were to continue this simulation even longer, eventually all the tigers would die out. So, we also ran a series of experiments in our virtual world to see how changing the animal's parameters affects their chances for success. In each experiment, we keep the initial setup of the world, the location of the terrains, and the animals the same. For example, here are some of the plots that we obtain from a given experiment. We can see the steps that each of the species survives on average, and the different causes of death for each of the species. We also experimented with implementing a genetic algorithm in the form of mating. Animals reproduce via this genetic algorithm, which features crossover and mutation. Here is a list of the parameters that can vary between the parents and the child. For instance, there is a hunger threshold, which refers to how hungry the child can get before it has to eat again. A high threshold is desirable, but not too high, otherwise the animal might not have time to seek food. So, that's it for Dynamic World. We hope that you enjoyed listening to it, as we certainly did enjoy creating it.